Okay, so the instructions up here look fairly cluttered, but they're the exact same ones that are in the notes posted directly above this link. So look there, don't look at this mess. But in case anybody's coming directly to this YouTube link, I wanted to write out the problem up here. So we've got a region bounded by the graphs of y equals the square root of x, which I've drawn in blue here, y equals 0, which is the x-axis, so I kind of traced over it in black, and then x equals 4, so this vertical line here. So here's your enclosed two-dimensional region. Now, imagine we take that region and revolve it about, so I'm going to revolve about the x-axis first. So we revolve it here. Then if you take this two-dimensional region here and revolve it, what you're going to get is, I mean, it looks kind of like the plug that you would use to plug a drain. Sort of what I picture. You get this sort of shape. We wish to find the volume of that solid. The plan is similar to the approach you take in Cal 1 to find, let's say you want to find area of this region in Cal 1. So the way integrals are introduced to you in Cal 1 is we look at this region. In this case, we have x going from 0 to 4. Take that interval and divide it up into a bunch of little subintervals. And then each of these subintervals corresponds to a rectangle whose height is determined by this square root of x function up here. So the height's determined by this function that we're finding area under, if you want to look at it that way. So this is just one of those rectangles. I don't want to draw all of them because the illustration gets way too cluttered. And so we do a lot of this in 7.2 and 7.3. I'll refer to the typical rectangle, which is what I'm drawing here, just one random rectangle in that whole infinite sum. So now imagine you take that rectangle, the one rectangle now, and revolve it. Then that would form a cylindrical disc. And maybe you've seen the animations that I linked to in the notes, so you don't have to put up with my drawing here, but something like this for that what turns out being a cylindrical disc that's formed when you revolve that rectangle. Maybe drawing it within this three-dimensional sketch. So if here's your typical rectangle and then it's revolved, it's going to give you this one like I said, cylindrical disc. Now, if we add up the volumes of all those cylindrical discs, it gives us the approximate volume of the entire solid. And then you take the limit as the number of rectangles approaches infinity, which is when the sum becomes an integral. When you take the limit as it approaches infinity, and it'll give us the exact volume of this solid. Now, so the volume of one of these discs, if you pick this disc up, set it on the table in front of you, it looks like this. So the height of the disc is the width of the rectangle here, which we call dx. So this thin width of the disc is dx. So again, imagine I'm picking up this disc and then setting it on the table in front of me. So in order to find the volume of this solid, we would need the height. I would also need the radius, which I'll call r here. And then the volume of a cylinder is pi r squared times the height, which in this case is dx. And then when you take the sum of all of the rectangles, take the limit as it approaches infinity, this becomes an integral. In this case, as x goes from 0 to 4, of this pi times the radius squared. So the real issue when you're working these problems is going to be determining what the radius is. So this formula is set. You're going to use this formula every time you're applying the disk method. You're using this formula. So this is not something you're going to have to recreate from scratch every single time. You're going to go straight to, okay, I can see that when I revolve one of these rectangles, it's going to form that disk shape. And so I know with disk method, volume is equal to pi. We should note is a constant coefficient, so I like to put that out in front of the integral. So pi times the integral, in this case from 0 to 4, of the radius squared dx. And then, so I'm still avoiding the issue, what's the radius? Like I said, that's the real question. So the radius of this disk is actually, it would be this distance here, right? Because the disk is sitting sideways here. But so the radius, like I said, of this cylindrical disk is this distance here, which if it's a vertical distance like this, it's the difference in the y values. So up here along the curve, y equals the square root of x. Down here on the x-axis, y equals 0. And so the radius, this distance, will be the difference between those y values. So in this case, let me get the eraser so I can see, we don't need that anymore. In this case, that radius is vertical distance, so we can do top minus bottom. Square root of x on top minus 0 on the bottom. So the radius in this case is just square root of x. And so our definite integral that gives the volume of this solid is pi integral from 0 to 4 of the square root of x squared dx. Which, yeah, so now we could make that x, and then we could integrate this fairly easily. In the homework, there's an instruction that says setup only. So that's telling you that you can actually just get to this point and stop. Because the integration is pretty straightforward in all of these problems, and it can be pretty exhausting if you do a whole bunch of them to fully integrate all of these, what I really want you to focus on when you're practicing is figuring out how to set up this definite integral that would give you the volume, and not so much to go through the mechanics of evaluating the integral. So you can stop here. Same thing on your exam 1. I'll just ask you guys to set up the definite integral, so you'll be able to stop at this point. For volumes, for area in 7.1, I do want you to fully evaluate those integrals just to get some practice, and to make sure that you understand, how it is fully solved, how these problems are fully solved, but in this case you can leave it. Okay, so this is the answer to part A. I want to address part B here. So what if it's revolved about the line y equals -1? This picture's too messy now, so I gotta get rid of it. I think I'll write the answer to A right here, though, just for the record. Okay, so now suppose, so I want to color code this again. So here's the graph of y equals square root of x, and then x equals 4 is a boundary here, and y equals 0 is a boundary here. And now we're taking that region and revolving it about the line y equals -1 down here. Same sample rectangle here. So now notice you've got this empty space between the axis of revolution and where your region stops. So when that happens, we're actually using a slightly different method here. So when you revolve it, you're going to get this, you're going to have a hole in the middle, right, of your solid. This is where, so I've got links to some animations because I know how difficult it is to rely on my drawings. So look at the animations that I've linked to in the notes. But what I want to show here is just that you have a hole in the middle. That's all I'm trying to argue. And so the shape you get, if we pick this up and set it on the table in front of you, it looks like a washer that you might use to, build a piece of furniture at home. Something like that. It's going to be a very thin, call it a disc, with a hole in the middle. So when you generate this sort of shape, you're actually using what we call the washer method. In order to find the volume of this solid, it's really just a disk minus a disk. We can find the volume of the outer cylinder. So let's see, outer, I'm going to abbreviate cylinder, minus the volume of the inner cylinder. If I call this, and forgive me if it doesn't match the other notation in the notes, but I like to call the radius of the outer cylinder, I like to use capital R, so big R for the radius of the outside cylinder, and then little r here for the radius of the inner cylinder. And so the volume of the outer cylinder will be, again, it's pi r squared times the height. So it's pi times big R squared times the height, which is this dimension here, which is dx again, in this case. Could also be dy here. Yeah, and it looks more like a dy the way I'm drawing it here. But the reason I know it's dx is if I go back to this, the width of the rectangle in my original illustration here is dx. Okay, and then inner cylinder, so it's pi r squared, but this time you're using the little radius, the little r, again times dx. And when you subtract that, notice that you could factor the pi out in front. Got too many markers in my hand. We could factor out the pi in front. We could factor out the dx in the back, and then inside we'll have outside radius squared minus inside radius squared. And so this is the gist of the washer method. And then you take the sum of all the rectangles with the limit as the number of rectangles approaches infinity. That's what turns this into an Riemann integral. Let's just put limits of integration a to b. And so this is your formula for the washer method right here, which is explained in more detail in the notes, by the way. Okay, but so now we need to refer back to this picture. So what's the outer radius? What's the inner radius? Well, the inner radius, let me get rid of this dx, would be this distance here, right? That's the radius of this inner cylinder. So this is the little r. Again, I mean, the way this is set up here, the inner radius happens to be, in this picture, it's a vertical distance. So it's the difference between the boundary up here, which is y equals 0, and the boundary down here, which is y equals -1. And so the difference between those boundaries is just 1. 0 minus -1, if you want to look at it that way. But so the inner radius, so no matter where we place this rectangle, the inner radius when you revolve these rectangles is always, it's just a constant 1. The inner radius is going to be just a constant. So let me make that note over here. So inner radius is 1. Now outer radius is the distance from the axis of revolution here to the outer edge of the region up here. So the outer edge of the region is along this boundary, y equals the square root of x. Axis of revolution is this, y equals -1. And so the outer radius, big R, is the difference between those. So it's top minus bottom. Difference between square root of x and -1. So that'll end up being the square root of x plus 1. And so using the washer method to answer part B, the volume is equal to pi times, again, the integral as x goes from 0 to 4. That's where all of our rectangles are going to lie, with x between 0 and 4, of outer radius, which is the square root of x plus 1, minus the inner radius, which is just that constant 1. All integrated with respect to x. So here's your answer to part B. And yes, I realize 1 minus 1, so it's going to cancel. And so, yikes-a-rama. Almost forgot. Sorry, guys. Outer radius squared minus inner radius squared, so I would have got away with that one. But this certainly would have caused problems not squaring this first part. So sorry, don't forget, it's your radius squared, pi r squared times the height. So this, okay, now is your correct answer for part B.